Look at a map of cell towers. Every house connects to the tower that is physically closest to it. When these physical coverage zones collide, they create rigid mathematical boundaries called a Voronoi diagram. Today, we are going to solve the classic Voronoi Villages programming problem by taking this exact geometric structure and placing it on a one-dimensional straight horizontal road. The problem gives us a road where 5 villages are located at specific coordinates: 16, 0, 10, 4, and 15. Our goal is to find the smallest neighborhood size among them. The prompt states these coordinates can fall anywhere from -1 billion to +1 billion. If you try to map this by creating an array with 2 billion empty slots, your program will crash instantly with a memory limit exceeded error. We only need to store the 5 specific coordinates provided. By ignoring the empty space on the road, we keep our memory footprint small and our logic focused. Looking at this diagram, notice the villages on the extreme left and extreme right. There is nothing blocking them on the outside. Their coverage neighborhoods project entirely to infinity. Since our objective is to find the absolute smallest neighborhood, an infinite territory will never be the correct answer. We can safely write off the outer edges and focus our calculations purely on the inner villages. Our raw data arrives out of order. A loop right now calculates distances between non-neighbors. But whenever handling one-dimensional spatial data, your first step is sorting. The villages snap into ascending order: 0, 4, 10, 15, 16. Now perfectly sandwiched between actual neighbors. With one standard sorting function, the spatial search becomes a linear traversal through an array. Let's calculate the size for village 4. The standard approach finds the left and right midpoints and subtracts them, yielding 5.0. Pause the video here. Look at these 3 formulas on the board. Can you combine them algebraically to remove the redundant variable? By combining fractions, we merge the calculations into a single equation. Look closely. The positive and negative versions of the current village's coordinate perfectly cancel each other out. The process collapses into one elegant formula: the right neighbor minus the left neighbor divided by 2. Removing the current village from its own calculation reduces the computational work needed inside your loop. Applying our optimized formula to village 10, the logic jumps straight from 4 to 15. 11 divided by 2 is 5.5. Since 5.5 is larger than our current minimum of 5.0, we move to the next village. We test our final village at 15. The right neighbor, 16, minus the left neighbor, 10, is 6. Divided by 2, we get 3.0. Since 3.0 is smaller than our previous 5.0, the scoreboard updates to our new minimum. Let's formalize the efficiency. Traversing the array takes O of n time, but the initial sorting step takes O of n log n time. Because the sort is the most intensive operation, our overall time complexity is O of n log n. Competitive judges are strict about output formatting. Even if your math results in a perfect integer, like 3, the solution will fail if it does not provide exactly 1 decimal place, 3.0. Solving these challenges comes down to spatial intuition, algebraic simplification, and strict adherence to technical formatting.